Hello everyone, I am Jannifer Padilla.
And I am lovely Quijada. In today's topic, we will tackle about routing concepts. So, let's begin!
Did you ever wonder what is router? And what does router do? Then, this is the right chapter for you. So, let us know first what is router. A router is a device that connects two or more packet switch network or subnetworks. It serves two primary functions: managing traffic between this network by forwarding data packets to their intended IP addresses, and allowing multiple devices to use the same internet connection. As we all know, networks allow people to communicate, collaborate, and interact in many ways. Networks are used to access web pages, talk using IP telephones, participate in video conference, compete in interactive gaming shop using the internet, compete online coursework, and more. Ethernet switches function at the data link layer. Layer 2 and are used to forward Ethernet frames between devices within the same network. However, when the source IP and destination IP addresses are on different network, the Ethernet frame must be sent to a router. A router connects one network to another network. The router is responsible for delivery of packets across different networks. The destination of the IP packet might be on web server in another country or an email server on local area network. The router uses its routing table to determine the best path to use to forward a packet. It is the responsibility of the routers to deliver those packets in a timely manner. The effectiveness of the internet works communication depends to a large degree on the ability of routers to forward packets in the most efficient way possible. When a host sends a packet to device on different IP networks, the packet is forwarded to default gateway because a host device cannot communicate directly with devices outside of the local network. The default gateway is the destination that routes traffic from local network to devices on remote networks. It is often used to connect a local network to the internet. As shown in this figure, there are many case structures and performance-related characteristics referred when discussing networks. Communication between networks would not be possible without a router determining the best path to the destination and forwarding traffic to the next router along the path. The router is responsible for the routing of traffic between networks. In the animation in this figure, the network topology diagram consists of two hosts, two switches, and two Cisco 1841 integrated series router or ISR. As I mentioned earlier, when a packet arrives on a router interface, the router uses its routing table to determine how to reach the destination of network. Most network-capable devices, that is computers, tablets, and smartphones, require these following components to operate: Central Processing Unit or CPU, Operating System or OS, Memory and storage, including RAM, ROM, and VRAM, flash, and hard drive. A router is essentially a specialized computer. It requires a CPU and memory to temporarily and permanently store data to execute operating system instructions such as system initializations, routing functions, and switching functions. The table in this figure summarizes the types of router, memory, the volatility, and the example of what is stored in each. Note: Cisco devices use the Cisco Internet Work Operating System or IOS as the system software. So, I will show to you the back panel of the router. As you can see, it contains some ports and more which are in this picture. Unlike a computer, a router does not have video adapters or sound cards adapters. Instead, routers have specialized ports and network interface cards to interconnect devices to other networks. Networking professionals know that it is the router that is responsible for forwarding packet from network to network, from original source to final destination. Most users are unaware of what the presence of numerous routers on their own network or on the internet. Users expect to be able to access web pages, send emails, and download music regardless of whether the server access is on their own network or on another network. Networking professionals know that it is the router that is responsible for forwarding packets from network to network, from the original source to final destinations. A router connects multiple networks, which means that it has multiple interfaces that each belongs to different IP network. The interface that the router uses to forward a packet may be the final destination, or it may be a network connected to another router that is used to reach the destination network. In this animation, the 1R1 and router 2 are responsible for receiving the packet on the one network and to forwarding the packet out another network towards the destination network. Each network that is a router connects to typically requires a separate interface. These interfaces are used to connect a combination of both local area network or LANs and wide area networks or WANs. Notice that each site in this figure 2 requires the use of a router to interconnect the other sites. Even the home office requires a router. In this topology, the router located at the home office is a specialized device that performs multiple services for the home network. Move forward. The primary function of a router are to determine the best path to send packets, forward packets toward their destination. The routing table includes the interface to be used to forward packets for each known network. When a match is found, the router encapsulates the packet into data link frame of the outgoing or exit interface, and the packet is forwarded toward its destination. It is possible for a router to receive a packet that is encapsulated in one type of data link frame and to forward a packet out of interface that uses different type of data link frame. In this animation, it follows a packet from the source PC to destination PC. Notice that it is the responsibility of the router to find the destination network in its routing table and forward the packet towards its destination. In this example, the router 1 receives the packet encapsulated in the Ethernet frame. After the de-encapsulating, the packet router 1 uses the destination IP address of the packet to search its routing table for matching network address. After the destination network address is found in the routing table, router 1 encapsulates the packet inside the PPP frames and forward the packet to router 2. A similar process is performed by the router 2. So, there are three packet forwarding mechanisms to support routers such as process switching, fast switching, and lastly Cisco switching forward, or CEF. The common analogy used to describe the three packet forwarding mechanism is process switching solves a problem by doing math longhand even if it is an identical problem. Fast switching solves a problem by doing math longhand and one time and remembering the answer for subsequent identical problems. CEF solves every possible problem ahead of the time in spreadsheet. Network devices and end users typically connect to a network using to a wired Ethernet or wireless connection. Refer to the figure as shown and sample reference typology. Also, the lines in the figure serves as an example of how users' network device could connect to network. As you can see, there is a home office in the left side and the branch side and in the lower part along with the central side, which are connected with their respective devices. In the branch and central LANs, hosts are connected either directly or indirectly via WAPS to the network infrastructures using layer 2 switch. To enable network access, devices must be configured with IP address information to identify the appropriate IP address identifies a unique host in a local network. Subnet mask identifies with which network subnet the host can communicate. Default gateway identifies the routers to send a packet to when destination is not on the same local network subnet. When a host sends a packet to a device that is on the same IP network, the packet is simply forwarded out of the host's interface to the destination device. When a host sends a packet to a device on a different IP network, then the packet is forwarded to default gateway. Because a host device cannot communicate directly with devices outside of the local network. The default gateway is the destination that routes traffic from local network to devices on remote networks. It is often used to connect a local network to the internet. The default gateway is usually address of the interface on the router connected to the local network. The router maintains routing table entries of all connected networks as well as the entries of remote networks and determines the best path to reach those destinations. Note: a router is also usually configured with its own default gateway. This is sometimes known as the gateway of last resort. When designing a network or mapping an existing network, document the network. At a minimum, the documentation should identify this following: device names, interfaces used in the design, IP addresses and subnet masks, default gateway, and addresses. As the figure shows, this information is captured by creating two useful network documents. Topology diagram provides a visual reference that indicates the physical connectivity. Logically, layer 3 addressing often creates using software such as MicroVisio, an addressing table, a table that captures device names, interface IPv4, address subnet masks, and default gateway addresses. A host can be assigned IP address information either statically or dynamically. Statically, the host is manually assigned correct IP address, subnet mask, and default gateway. The DNS server IP address can also configured, while dynamically IP address information is provided by a server using the Dynamic Host Configuration Protocol or DHCP. The DHCP server provides the valid IP address, subnet mask, and default gateway for end devices. Other information be provided by the server. Host computers connect to a wired network using a network interface and RJ45 Ethernet cable. Most network interfaces have one or two LED link indicators next to the interface. Typically, a green LED means a good connection, while a blinking green LED indicates network activity. If the link light is not on, then there may be a problem with either the network cable or the network itself. The switch port where the connection terminates would also have LED indicator lit. If one or both ends are not lit, try a different network cable. Note: the actual function of the LEDs varies between computers manufacturers. Similarly, network infrastructures devices commonly use multiple LED indicators to provide a quick status view. Cisco ISRS use various LED indicators to provide status information. A Cisco 1941 router is shown in the figure. The router help network administrator conduct some basic troubleshooting. Each device has unique set of LEDs and consult device-specific documentation of accurate description of the LED. In a production environment, infrastructure's devices are commonly accessed remotely using Secure Shell or SSH or Hypertext Transfer Protocol secures HTTPS. Console access is really only required when initially configuring a device or if remote access fails. Console access requires console cable, RJ45 to DB9 console cable, terminal emulation software, or TerraTerm, PUTTY, hyperterminal. The table in the figure summarizes the console connection requirements, display the figure ports and cable required. Network infrastructure devices requires IP addresses to enable remote management. Using the device IP address, the network administrator can remotely connect to the device using Telnet, SSH, HTTP, or HTTPS. A switch does not have dedicated interface to which an IP address can be assigned. Instead, the IP address information is configured on a virtual interface called Switch Virtual Interface (SVI). For example, in the figure, the SVI in the layer 2 switch SI is assigned the IP address 192.168.10.2/24 and the default gateway of the router located at 192.168.10.1. Use the syntax checker in the figure to configure the layer 2 switch and the S2. Cisco router and Cisco switches have many similarities. They have support a similar model operating system, similar command structures, and many of the same commands. In addition, both devices have similar initial configuration steps. Then, when configuring a Cisco switch or a router, following basic tasks should be performed first. Name the device, distinguishing it from other routers, secure management access, secured privilege, exec user, exec and telnet access, encrypts password to their highest level. Configure a banner, provides a legal notification and authorized access. Note: always save changes on a router, verify the basic configuration and the router operation. The device is named, management access is secured, and then in this figure, a banner configured, the configuration is saved. And lastly, in this figure, I'll use the syntax checker, configure the router too. There are several show commands that can be used to verify the operation and configuration of an interface. The following three commands are especially useful to quickly identify the interface status. Show IP interface brief. Display a summary for all interfaces including the IPv4 address of the interface and current operational status. Show IP root. Display the content of IPv4 routing table stored in RAM in Cisco iOS 15 active interfaces should appear in the routing table with two related entries identified by the code C connected or L local. In previous iOS versions, only a single entry with the code C will appear. Show running config interface display the command configured on the specified interface. In this figure, the output of the show IP interface bref command. And then, in this figure, display the output of the show IP root command. And another this figure, display the output of the show running configured interface command. In this figure, display to verify the interface on router 1. And next, the command to verify the IPv6 interface configuration are similar to the command used for IPv4. The figure shows IPv6 interface bref command in the figure 1 display a summary for each of the interfaces. The up output on the same line at the interface name indicate the layer of layer 2 interface state. This is the same as the status of the protocol columns in the equivalent of IPv4 command. The filtering of parameters that can be configured after the pipe include section shows entire section that starts with the filtering expression. Include includes all output lines that match the filtering expression. Exclude all output lines that match the filtering expression. And begin shows all the output lines from certain points starting with the line that matches the filtering expression. The command history feature is useful because it temporarily stores the list of executed commands to be recalled. To recall command in the history buffer, press Ctrl plus P or the up arrow key. The command out begins with the most recent command. Repeat the key sequence to recall the successively older commands. To return the more recent commands in the history buffer, press Ctrl N or down arrow key. Repeat the key sequence and recall the successively more recent commands. A primary function of router is to forward packets to forward their destination. This is accomplished by using switching function, which is the process used by a router to accept a packet on the interface and forward it out of another interface. A key responsibility of the switching function is to encapsulate packet in the appropriate data link frame type of outgoing data link. What does a router do with a packet received from network and destined for another network? The router performs the following three major steps. Step 1. De-encapsulate the layer 3 packet by removing the layer 2 from header to trailer. Step 2. Examine the destination IP address of the IP packet to find the best path the routing table. Step 3. If the router finds a path to the destination, it encapsulates the layer 3 packet into a new layer 2 frame and forward the frame packet in its interface. In the animation, the figure PC1 is sending a packet to PC2. PC1 must determine if the destination of IPv4 address is on the same network. The PC1 determines its own subnet by doing an operation its own IPv4 address and subnet mask. This produces the network address that PC1 belongs to. Next, PC1 does the same end operation using the packet destination of IPv4 address the PC1 subnet mask. If the destination network address the same network as the PC1, then the PC1 does not use the default gateway. Instead, PC1 refers to its ARP cache for the MAC address of the device with that destination IPv4 address. If the MAC address is not in the cache, then the PC1 generates an ARP request to acquire the address to complete the packet and send it to the destination. If the destination network address is on different network, then the PC1 forward the packet to default gateway. To determine the MAC address of the default gateway, PC1 checks the ARP table for the IPv4 address of default gateway and its associated MAC address. If an ARP entry does not exist in the ARP table for default gateway, PC1 sends an ARP request. Router 1 sent back an ARP reply. PC1 can then forward the packet to the MAC address of default gateway, then the if a 0 over 0 interface of router 1. The animation in the figure illustrates how the router 1 forward the packet to router 2.
The animation in the figure illustrates how the R2 forwards the packet to router 3.
The animation in the figure illustrates how the router 3 forward the packet to PC2.
We're now on path determination under routing decisions topic. Before we dive in, let's go back on defining router. It is to determine the best path to use to send packets. To determine the best path, the router searches its routing table for a network address that matches destination IP address of the packet. The routing table search results in one of three path determinations. First, directly connected network. If the destination IP address of the packet belongs to a device on a network that is directly connected to one of the interfaces of the router, that packet is forwarded directly to the destination device. This means that the destination IP address of the packet is a host address on the same network as the interface of the router. Remote network. If the destination IP address of the packet belongs to a remote network, then a packet is forwarded to another router. Remote networks can only be reached by forwarding packets to another router. Lastly, no route determined. If the destination IP address of the packet does not belong to either a connected or remote network, the remote determines if there is a gateway of last resort available. A gateway of last resort is set when a default route is configured on a router. If there is a default route, the packet is forwarded to a gateway of last resort. If the router does not have a default route, then the packet is discarded. If the packet is discarded, the router sends an ICMP, or also known as Internet Control Message Protocol, an available message to source IP address of the packet. The logic flowchart in the figure illustrates the router packet forwarding decision process. Next up, path determination. Determining the best path involves the evaluation of multiple paths on the same network destination and selecting the optimum or shortest path to reach that network. Whenever multiple paths on the same network exist, each path uses a different exit interface on the router to reach that network. The best path is selected by a routing protocol based on the value or metric it uses to determine the distance to reach a network. A metric is a quantitative value used to measure the distance to a given network. The best path to a network is the path with the lowest metric. Dynamic routing protocols typically use their own rules and metrics to build and update routing tables. The routing algorithm generates a value or a metric for each path through the network. Metrics can be based on a single characteristics or several characteristics of a path. Some routing protocols can base route selection on multiple metrics, combining them into a single metric. Moving on, the following list are some dynamic protocols and the metrics they use. First, we have RIP, which stands for Routing Information Protocol, defined as hop count. Second is the Open Shortest Path First, or OSPF, defined as Cisco's based on cumulative bandwidth from source to destination. Lastly, the Enhanced Interior Gateway Routing Protocol, or EIGRP, defined as bandwidth, delay, load, and reliability. We are now down to load balancing. The animation you can see is an example of equal cost load balancing. When a router has two or more paths to a destination with equal cost metrics, then the router forwards the packets using both paths equally. The routing table contains the single destination network but has a multiple exit interfaces, one for each equal cost path. The router forwards packet using the multiple exit interfaces listed in the routing table. If configured correctly, load balancing can increase the effectiveness and performance of the network. Equal cost load balancing can be configured to use both dynamic and routing protocols and static routes. Note that only Enhanced Interior Gateway Routing Protocol supports equal cost load balancing. We're now on the last subtopic under path determination, which is administrative distance. It is possible for a router to be configured with multiple routing protocols and static routes. If this occurs, the routing table may have more than one route source for the same destination network. For example, if both RIP and EIGRP are configured on a router, both routing protocols may learn of the same destination network. However, each routing protocol may decide on different paths to reach destination based on that routing protocol's metric. RIP chooses a path based on hop count, whereas EIGRP EIGRP chooses a path based on its composite metric. The table or the photo shows the list of various routing protocols and their associated ADS. Cisco IOS uses what is known as the administrative distance or AD to determine the route to install into an IP routing table. The AD represents the trustworthiness of the route. The lower the AD, the more trustworthy the route source. For example, a static route has an AD of 1, whereas an EIGRP discovered route has an AD of 90. Given two separate routes on the same destination, the router chooses the route with the lowest AD. When a router has the choice of a static route and an EIGRP route, the static route takes precedence. Similarly, a directly connected route with an AD of 0 takes precedence over a static route with an AD of 1. The next topic that I'm going to tackle is about router operation. Under this topic, it includes analyze the routing table, directly connected interfaces, statically learned routes, and dynamic routing protocols. First, the routing table of a router stores information about directly connected routes. These routes comes from the active router interfaces. Routers add a directly connected route when an interface is configured with an IP address and is activated. Second, remote routes. These are remote networks connected to other routers. Routes to these networks can either be statically configured or dynamically configured using dynamic routing protocols. Specifically, a routing table is a data file in RAM that is used to store route information about directly connected and remote networks. The routing table contains network or next hop associations. These associations tell a router that a particular destination can be optimally reached by sending the packet to a specific router that represents the next hop on the way to the final destination. The next hop association can also be outgoing or exit interface to the next destination. The figure identifies directly connected networks and remote networks of the router R1. Routing the table sources. On a Cisco IOS router, the show IP route command can be used to display the IPv4 routing table of a router. A router provides additional route information including how the route was learned, how long the route has been in the table, and which specific interface to use to get the predefined destination entries in the routing table. Can be added as first, local route interfaces, added when an interface is configured and active. This entry is only displayed in iOS 15 or newer or IPv4 routes and all iOS releases for IPv6 routes. Next, directly connected interfaces, added to the routing table when an interface is configured and active. Next is static routes, added when a route is manually configured and the exit interface is active. Lastly, dynamic routing protocol, added when a routing protocols that dynamically learned about the network, such as EIGRP or OSPF, are implemented and networks are identified. Now we move on the routing table sources. The sources of the routing table entries are identified by a code. The code identifies how the route was learned. For instance, common codes include first L, identifies the address assigned to a router's interface. This allows the router to efficiently determine when it received a packet for an interface instead of being forwarded. Second, the letter C, identifies a directly connected network. S identifies a static route created to reach a specific network. D for identifies a dynamically learned network from another router using EIGRP. Lastly, the letter O identifies a dynamically learned network from another router using the OSPF routing protocol. Note that other codes are beyond the scope of this chapter. Next, remote network routing entries. It is critical for a network administrator to understand how to analyze the contents of IPv4 and IPv6 routing table. The figure shows an entry in IPv4 routing table on R1 for the route to distant network 10.1.1.0. In the figure, it has color-coded on which part is being described for us to be able to know easily. To continue remote network entries, the following information identifies entry. First, we have root source. It identifies how the route was learned. Second, destination network identifies the address of the remote network. Next is administrative distance, identifies the trustworthiness of the root source. Lower values indicate preferred root source. Next is metric, identifies the values assigned to reach the remote network. Lower values indicate preferred routes. Next is next hop, identifies the IPv4 address of the next router to forward the packet to. Second to the last is route timestamp, identifies how much time has passed since the route was learned. Lastly is outgoing interface. It identifies the exit interface to use to forward a packet toward the final destination. Next topic is about directly connected interfaces. A newly developed router without any configured interfaces has an empty routing table, as shown in the figure. Before the interface state is considered up or up and added to IPv4 routing table, interfaces must be assigned a valid IPv4 or IPv6 address. Next, it must be activated with no shutdown command. Lastly, it must receive a carrier signal from another device, which are router, switch, host, and etc. When the interface is up, the network of the interface is added to the routing table as directly connected to the network. In connection with directly connected interfaces, an active, properly configured, directly connected interface actually creates two routing table entries. The figure displays the IPv4 routing table entries on R1 for directly connected network 192.168.10.0. The routing table entry is directly connected interfaces is simpler than the entries for remote networks. The entries contain root source, destination network, and outgoing interface. In this slide, it shows the example in figures 1 to 3 show the steps to configure and activate the interfaces attached to R1. Notice that layer 1 and layer 2 informational messages generated as each interface is activated. As each interface is added, the routing table automatically adds to connected as C and local as L entries. Moving on. In this figure number 4 provides an example of the routing table with the directly connected interfaces of R1 configured and activated. On the last part of the sequence figures, it used the syntax checker to configure and activate the interfaces connected to R2. We're now down to the last subtopic, under directly connected interfaces, which is directly connected IPv6 examples. The examples in Figure 1 shows the configuration steps for directly connected interfaces of R1 with the indicated IPv6 addresses. Notice that the Layer 1 and Layer 2 informational messages generated as each interface is configured and activated. Go on the next figure, which is the Figure 2. It shows that the IPv6 root command show is used to verify that IPv6 networks and specific IPv6 interface addresses have been installed in the IPv6 routing table. Like IPv4, a C next to a root indicates that it is directly connected to a network. An L indicates the local root. In an IPv6 network, the local root has /128 prefix. Local roots are used by routing tables to efficiently process packets with a destination address of the interface of the router. Notice that there is also a root installed, the FF00 /8 network. This root is required for multicast routing. Go on the next figure, which is the Figure 2. It shows that the IPv6 root command show is used to verify that IPv6 networks and specific IPv6 interface addresses have been installed in the IPv6 routing table. Like IPv4, a C next to a root indicates that it is directly connected to a network. An L indicates the local root. In an IPv6 network, the local root has /128 prefix. Local roots are used by routing tables to efficiently process packets with a destination address of the interface of the router. Notice that there is also a root installed, the FF00 /8 network. This root is required for multicast routing. The following Figure 3 displays how the show IPv6 root command can be combined with a specific network destination to display the details of how that root was learned by the router. We're now down to the last figure of directly connected IPv6 example. As you can see in Figure 5, notice what happens when G0/0 LAN interface of R2 is target of the ping command. The pings are unsuccessful. This is because R1 does not have an entry in the routing table to reach 2001:DB8:ACAD:4:/64 network. R1 requires additional information to reach a remote network. Remote network root entries can be added to the routing table using either static routing or dynamic routing protocols, which of these two will be discussed on the following slides. Now, let's go on to the next topic, the statically learned routes. Now, after directly connected interfaces are configured and added to the routing table, then static or dynamic routing can be implemented. Let me first expound what is static routes. Static routes is manually configured. They define an explicit path between two networking devices. The benefits of using static routes include improved security and resource efficiency. Static routes use less bandwidth than the dynamic routing protocols, and no CPU cycles are used to calculate and communicate routes. But, however, the main disadvantage to using static routes is the lack of automatic reconfiguration if the network topology changes. For example, you're from LAN and you will transfer to WAN. It means that you will having be a small problem in reconfiguration the network. Next, there are two common types of static routes in the routing table. First is the static route to a specific network. Second is default static route. A static route can be configured to reach a specific remote network. IPv4 static routes are configured using the IP route, global configuration command, and identified in routing table with the code S. While the default static route is similar to a default gateway on a host. It specifies the exit point to use when the routing table does not contain a path for destination network. It is useful when a router has one exit point to another router, such as when the router connects to a central router or service provider. We're now on static routes examples. The figure shows the configuration of an IPv4 default static route. On R1, the serial 0/0/0 interface. Notice that the configuration of the route generates an S** entry in the routing table. The S signifies that the route source is the static route, while the asterisk identifies this route as a possible candidate to be the default route. In fact, it has been chosen as the default route as evidenced by the line that reads, "Gateway of last resort is 0.0.0.0 to network 0.0.0.0. For static routes examples, the image shows the configuration of two static routes from R2 to reach the two LANs of R1. The route to 192.168.10.0/24 has been configured using the exit interface, while the route to 192.168.11.0/24 has been configured using the next hop IPv4 address. Although both are acceptable, there are some differences in how they operate. For instance, notice how different they look in the routing table. Also, notice that because of these static routes were to specific networks, the output indicates that the gateway of last resort is not set. Lastly, like IPv4, IPv6 supports static and default static routes. They are used and configured like IPv4 static routes. To configure a static default IPv6 route, use the IPv6 route global configuration command. We finally hop on the last lesson under this chapter, the dynamic routing protocols. Dynamic routing protocols. Dynamic routing protocols are used by routers to share information about the reachability and status of the remote networks. Dynamic routing protocols perform several activities, including network discovery and maintaining routing tables. Network discovery is the ability of a routing protocol to share information about that network know about with other routers that are also using the same routing protocol, instead of depending on manually configured static route to remote networks on every router. A dynamic routing protocol allows the routers to automatically learn about these networks from other routers. These networks and the best path to each are added to the routing tables of the router and identified as a network learned by a specific dynamic routing protocol. During a network discovery, routers exchange routes and update their routing tables. Routers have converged after they have finished exchanging and updating their routing tables. Routers then maintain the networks in their routing tables. In this slide, you can see a picture or a figure that provides a simple scenario of how two neighboring routers could initially exchange routing information. In this simplified message, exchange R1 introduces itself to networks it can reach. R2 responds and provides R1 with its networks. We are now on the second subtopic of dynamic routing protocols, which is the IPv4 routing protocols. A router running a dynamic routing protocol does not only make a best path determination to a network, it also determines a new best path if the initial path becomes unusable or if the topology changes. For these reasons, dynamic routing protocols have an advantage over static routes. Routers that use dynamic routing protocols automatically share routing information with other routers and compensate for any topology changes without involving the network administrator. Cisco ISR routers can support a variety of dynamic IPv4 routing protocols, including EIGRP, that stands for Enhanced Interior Gateway Routing Protocol. Second, the OSPF, or the Open Shortest Path First. This two is what I mentioned earlier in the previous slides. And the third is ISIS, Intermediate System to Intermediate System. Fourth and lastly would be the RIP, the Routing Information Protocol. To determine which routing protocols are supported by iOS, use the router ? command in global configuration mode as shown in the figure. Next up is IPv4 dynamic routing examples. In this dynamic routing example, assume that R1 and R2 have been configured to support dynamic routing protocol EIGRP. The routers also advertise directly connected networks. R2 advertises that it is the default gateway to another networks. The output in the figure displays the routing table of R1 after the router have exchanged updates and converged. Along with the connected and linked local interfaces, there are 3 D entries in the routing table. The entry begin with D**EX identifies that the source of this entry was EIGRP, or also known as D. The root is candidate to be default root **, and root is an external root as *EX forwarded by EIGRP. The other 2D entries the roots installed in the routing table based on the update from R2 advertising its LANs. Next, the second topic before this chapter ends, the IPv6 routing protocols. ISR routers can support dynamic IPv6 routing protocols, including RIPNG or RIP Next Generation, OSPFv3, and lastly, the EIGRP for IPv6. Support for dynamic IPv6 routing protocols is dependent on hardware and iOS version. Most of the modification in the routing protocols are to support the longer IPv6 addresses and different header structures. To enable the IPv6 routers to forward traffic, you must configure the IPv6 unicast routing global configuration command. We are now finally on the last topic for this chapter, which is the IPv6 dynamic routing examples. As shown in the image, routers R1 and R2 have been configured with dynamic routing protocol EIGRP for IPv6. To view the routing table on R1, enter the Show IPv6 Route command, as shown in the figure. The output in the figure displays the routing table of R1 after routers have exchanged updates and converged. Along with the connected and local routes, there are 2D entries, which is the EIGRP routes in the routing table. To sum up everything on this chapter, here are the summary. When discussing networks, topology, speed, cost, security, availability, scalability, and reliability is being mentioned often. Cisco routers and Cisco switches have many similarities. They support a similar modal operating system, similar command structures, and many of the same commands. Third, the main purpose of the router is to connect multiple networks and forward packets from one network to the next. Next up is Cisco IOS uses what is known as the administrative distance or AD to determine the routing installed into the IP routing table. Next, remote networks are added to the routing table in two ways, either by the static routes or dynamic routing. Next, dynamic routing protocols automatically adjust to changes without any intervention from the network administrator. Next, routers makes their primary forwarding decision at layer 3, the network layer. Second to the last is the Cisco IP routing table is not a flat database. Lastly would be components of the IPv6 routing table are very similar to the IPv6 routing tables. This is the end of CCNA 2 Chapter 1 Routing Concepts. And note that the static and default routes will be discussed in details on the following reporters. That's all. Thank you for watching.